Hey guys, I'm a verified educator at Unacademy, and along with that, I'm also teaching live at Unacademy Plus. To access my live classes, you can take Unacademy Plus subscription. Now, Unacademy Plus offers some interesting features apart from live classes, which include detailed and complete explanation of a particular course. Then there you have problem discussion for self-evaluation. You can also watch recorded version of the class in case if you miss out any live session. You have regular doubt clearing sessions for doubt clearing and to clarify all your problems. You also get access to the WhatsApp group to clear and discuss problem among the other plus students. Now, if you have found these features interesting and want to join Unacademy Plus, I'll recommend you to use my referral code that is n_huda to get 10% discount on the subscription fee. Now that's all about Unacademy Plus. Let's continue with our video. Hey guys, hello everyone and welcome to the channel. So this video is going to be about the kinetics of photochemical reactions, right? Now photochemical reactions, as you all know, photochemical reactions means a reaction which is like the reaction which is initiated by the photons, right? Like light initiated reactions, or the reactions which depend upon that how much light you shine on that, and like that kind of reactions are basically called as photochemical reactions, right? Now in this video we'll be dealing with the kinetics part of that. Now this is again a part of your chemical kinetics, and we have already done a lot of videos on chemical kinetics. I have a whole series of videos on chemical kinetics. I'll give you link of that over here. Okay, you can watch like by clicking on this I button, and you can watch the whole playlist. All the videos related to chemical kinetics are over there, and by watching that, this particular topic will be covered by you guys. Okay, so we'll be dealing with the chemical kinetics part of photochemical reaction. So this video you will understand in more detail if you have basic knowledge of writing rate law equation using a steady state approximation, and if you have knowledge of like if you are given, like if you have that knowledge that if a particular reaction is given and you are able to find out the rate law equation, or the rate of the equation depend like based upon the concentration of a particular thing, then you will understand this video more well. Okay, so if you don't know those things, I'll suggest you to watch these videos in the playlist and then come back to this particular video to understand it in more detail. Okay, so this particular photochemical reaction is like this is not at all different than a usual chemical reaction. There is just a little bit difference in the reaction or in the species. Okay, I'll just let you know that how actually it, like what is the actual difference over here. Okay, so let's understand with the help of example over here. So the example is about the photo decomposition of Hi, that is hydrogen iodide. So hydrogen iodide will decompose into hydrogen gas and iodine gas in the presence of light. Okay, so you need H nu over here. So how this happens, this is the mechanism over here. So Hi, when you treat it with this when the photon falls on it, so it will form two radicals like hydrogen radical and iodine radical. Then your two, like when the Hi molecule interact with the hydrogen radical, it will form hydrogen gas plus iodine radical. Two iodine radicals will combine together to form I2, and this metal over here will behave as a quencher, and it will just like it will just absorb the excess energy to form the metal excited state. Okay, metal in the excited state. So that's what this photo decomposition of Hi actually looks like. So how to write down the rate of this reaction? Okay, so like see, for the first step, if I write down, so your rate of formation of, let's say, like dHi by dt means the rate of decomposition of Hi by dt, that how much this will decompose. Okay, that will depend upon the I absorbed, means how much, like I means intensity and abs means absorption. So how many intensity of light has been absorbed. So the more light will be absorbed, the more decomposition of Hi will be done. This negative sign is telling you that Hi is being decomposed. Okay, Hi will be decomposed. You can also write down this equal to like dH radical by dt. Okay, that also you can write down, but because that is in the positive form, because H radicals are being formed in this step. Okay, or I radical by dt, that also you can write down, but the decomposition of Hi depends upon I absorbed. That's what I wanted to tell you. In the second step, if you write down this like minus dHi by dt, that will be equal to, this is the rate constant, this is the rate constant k1, so that will be like k1, since it's in the decomposition part, like negative part, so it will be like k1 hi and into h radical. Okay, so that's how you will write down the rate or like rate equation for this step. Now for the second step you can use again, like here you don't have hi, so basically you don't need to do that. Okay, so yeah, these are the two steps which you can write down, and this is how you will like the overall decomposition of your dhi by dt. This will depend upon I absorbed, means the intensity of light which will be absorbed, plus k1 hi and h radical. Okay, so that's what the overall rate of decomposition of hi with respect to time will like the rate of decomposition of hi will look like. Okay, so this is the basic thing, this is the basic idea which I just wanted to tell you, that how this I absorb come over here. So I absorb is nothing but in the step where you will be having, you will find out a photon, or in the reaction if it is given like h nu, that means this reaction depends upon this for the intensity of photon being in absorbed. So that means this whole rate of reaction depends upon now intensity of photon that is being absorbed, so I absorbed, so that's why it is written like this. So this is the basic idea. Okay, I just wanted to tell you like with the help of a basic example. Now let's talk about some common representations. Okay, now these are some very common representation of different photochemical processes. So if the absorption happens, just now we have seen, so what happens in the absorption, you will see h nu along with that metal, and like the metal will go in the excited state or whatever it is. So like here it's just the photochemical excitation of the metal, so it's given like m plus h nu is giving you m star. So the rate for this step will be written like this. So rate will be equal to, actually this will be equal to your I absorbed, so it will be proportional to your I absorbed, that how much intensity is being absorbed. Okay, so that is because this is the absorption process where this photon is being absorbed, and how much photon will be absorbed, that will only tell you, that will only enhance or decrease the rate of the reaction. Okay, now the second process is fluorescence process. This is the just the reverse process of the absorption process. Here this excited metal metal in the excited state will lose its energy in the form of photon and in the form of that metal back. Okay, so it might happen that the frequency of both these photons are same, or it might be different, that doesn't matter. But yeah, this is how it is represented, your fluorescence. Generally we write down mu f, that means fluorescence frequency. So it will be written like, the rate for this reaction will be written like this, kf, if the rate constant for this reaction is kf, so kf into m star. Okay, so it's just the general way of writing the rate law equation for this reaction. Third one is your internal conversion. We have seen that in the Jablonski diagram, internal conversion is being done when the metal in the excited state loses its energy like through the vibrational and the other relaxations, and it comes to the ground state, right? So that's what it happens over here. So the k, if the rate constant for this is represented by KIC, so the rate will be given by this, that is KIC and your metal in the excited state. So this will be the rate for the internal conversion reaction. The last one is inter-system crossing. Now over here what happens, that the metal remains in the excited state, but the spin changes. It changes its spin from the singlet state to the triplet state. So the rate for this will be given by if the rate constant is KISC inter-system crossing, so it will be KISC, and in the bracket it will be like m star s. Okay, the singlet one. So that's how the common representations are given there. I have just given you so that whenever question is asked in the exam, you don't you don't get confused anywhere, right? So now we'll be taking up some questions which were already asked in CSIR NET exam, and we'll see that how to solve them. Before going into the question, there is one more like small topic. Let me just introduce you guys with that. So there is a very small and very interesting concept of quantum yield over here. Quantum yield tells you that how many how many number of, or how many amount of your reactants are actually getting converted into the product depending upon the intensity of light which is being absorbed. So it actually tells you that if you are shining a particular amount of light on a particular like reactant to form product, so how much reactant is being formed. So that's what your quantum yield tells you, right? So quantum yield is denoted by this Greek letter phi. So phi is equals to rate of process divided by the intensity of light absorbed. So generally we just write down the rate value, whatever the rate of the reaction is, divided by the I absorbed value, and that the ratio of both of them will give us quantum yield. The more quantum yield, the better photochemical reaction, we say. Okay, so that's what a very important concept was left out. Now let's go to the question and just see that how to solve them out. Alright, so now let's discuss this question which was asked in CSIR December 2017, and it was asked for 4 marks, right? The question says that the photochemical decomposition of Hi, that is hydrogen iodide, takes place with the following mechanism. Mechanism is given to you that Hi reacts with your, like, it takes the photon, and Ia is the intensity of the absorbed photons, and it gives you H and I. Then H and H, like H react with the Hi with a rate constant K1 to give you H2 plus I, and then these two I react with this metal quencher to give you like K with the rate constant K2 to give you I2 plus M. Now this is nothing but what we have seen just now, okay? Just the example which we have taken, it's the same thing given in a different way. It says that considering hydrogen, that is hydrogen, concentration of hydrogen and iodine atom as the intermediates, the rate of removal of Hi. So they are asking about the rate of removal of Hi. Okay, that means what they are asking is minus dHi by dt. Okay, so removal of Hi. So just you have to look upon those steps first of all in which Hi is given there. So these are the two steps in which Hi is there. In this step, in the third step, we don't have Hi. So we don't have to deal with the third step. We just have to deal with the two steps in the first and second option. Okay, first and second lines. Now the decomposition of this Hi, first of all, it will depend upon the intensity of light absorbed, or Ia or I absorbed. Why? Because the more photon you give, the more Hi will react with it to get converted into H plus I. So the decomposition of Hi, that is minus dHi by dt, that depends upon what? That depends upon the intensity of photon which is used. So that's why it is equals to I absorbed plus. Now this Hi is on the reactant side. So since it is on the reactant side, so that's why I write down plus sign, and then we will write down this in the rate constant term. So on the reactant side we have what? So this will be like K1, and we will be having H, and we will be having Hi. Basically it should not be just H, it should be H radical, but fine, that's fine. This is how it will be written as. Okay, so that's what your equation it will come out to be. Now we have to apply, so this is what it is, but this is a intermediate, right? So we have to apply steady state approximation on that intermediate. So let's try to do that. So on applying steady state, okay, so let's find out first of all dH by dt, and that is equals to our minus K1 H into Hi, and where do we have the second one? So that is equal to, like in the here, so the formation of dH by dt, that depends upon like how much hydrogen ion will be formed, that will also depend upon the I absorbed. So plus I absorbed. Now just see that how I have written this equation. I have not written negative sign over here, I have written positive sign. That means here I am looking upon the formation of hydrogen radical. So where your hydrogen radical will be formed, that's what I am looking upon. Now in the first step, hydrogen radical will be formed if I increase the intensity of photon over here. So that's why it depends in a positive way on this I absorbed. So that's why I have written it in the positive form. But here in the second step, the intensity, the rate of formation of DH, but here this hydrogen is actually not on the formation side. This is called formation side or the product side. This is on the reactant side. That means it will react and it will decompose. So since the concentration will decrease after every regular interval of time, that's why I have taken it as negative. So negative sign tells you that this hydrogen ion is actually getting decomposed in this reaction, although we are looking into the formation of this. So that's why I have written like this, negative part over here and positive part over here. Now just let's quickly understand this again, that why I have written this like this, because here we have to look upon to the rate of removal of Hi. Okay, that's what is given in the question. That means we need to find out the rate of decomposition of HI. That means we have to find out minus dHI by dt. So how HI will decompose, that depends upon like the intensity of light which you are using. Okay, so the intensity of light which you are using, the more intense light you use, the more decomposition will take place. So that's why I absorbed is here in the positive sign. Now in the second step, we are looking upon to the decomposition of HI, means how easily it is getting decomposed. So that depends, like since it is getting decomposed only in the second step, it's not forming, see it's decomposing it to H2 and I. So that's why we have written it in the positive form, because we are looking upon the decomposition of HI and decomposition is also happening. That's why we have written positive. So whatever we are looking upon, if the same thing happens, we write down plus sign. If whatever we are looking upon, if the opposite thing happens, we write down negative sign. So we again just reconfirm this, that why we have written negative sign, because we were looking upon to the formation of HI, because with the positive sign tells the formation of HI, but sorry, formation of H, but here H is getting decomposed. See, H is getting decomposed to H2, so H is not getting formed in the second step. That's why we have written negative sign. I hope this is much clear that why we have written plus and minus sign. Alright, so now let's so this is what it is. So the rate of H is will be given by this. So this is an intermediate, so we can apply steady state approximation. So on applying steady state approximation, what we can say that dH by dt or dH radical by dt, that is equals to 0, means rate of formation of this intermediate is equals to 0. Let's put the value. So minus k1 H into HI plus IA is equals to 0, that's I. Okay, so IA is equals to 0. So what does that mean? It means that k1 H into HI will be equal to IA. So this is equation 2, this is equation 1. So from equation 1 and 2, what we can write down? So from equation 1 and 2, we can write down that minus dH I by dt. Okay, this is I. Okay, so dH, I'll just write down it again. So minus dHi by dt, this is A absorbed or IA. Okay, plus whole value of this thing we just got IA, so plus IA. So IA plus IA will give you 2IA. So the answer should be 2IA. Now you look upon to the option. In the option you have option number C. So option number C tells you that the rate of removal of HI will be 2IA. Now one more thing it can be asked, that if you want to calculate, okay, it's not actually asked, but if you want to calculate the quantum yield, how you will do that? So quantum yield will be given by this formula, that is phi. So rate by I absorbed. So rate is 2IA divided by IA. So IA will be cancelled out, you will get 2. So 2 will be the quantum yield for this particular reaction. Okay, so I hope this is much clear to you guys that how we have done this. You just need to practice a few questions on this, and you will be well practiced and well prepared for this particular topic. Now let's go to the next question, which was asked in June 2019 exam. Alright, so let's talk about this particular reaction which was asked in CSIR June 2019 exam. And the question was actually like based upon the same concept, the photochemistry of the kinetics of photochemical reaction. So the reaction, the question says that the photochemistry of molecule M is described as by the mechanism. This is the mechanism. M is the molecule. In the first step, it absorbs photon and get converted into the excited state. The rate of the reaction is given by I absorbed. Then the second step, it reacts like M star in the excited state. M reacts with Q to give you M plus Q. Okay, and this is this is the rate for that particular step. And the third step is in where your M in the excited state get converted back into the ground state by releasing a photon of h mu f with the frequency mu f, and the rate is given by 0.2 M star. So by looking upon to the options and just recalling whatever I have taught in this video, you can say that the first step is absorption step, and the last step is nothing but your fluorescence step, right? So this is fluorescence, this is absorption. Now it's given that the intercept at Q is equals to 0 is 4 for the inverse of the fluorescence intensity. Inverse of the fluorescence intensity value, like inverse of the fluorescence intensity, that is 1 upon IF. Okay, that's 1 upon IF versus Q plot. Okay, so if you are plotting 1 by IF versus Q plot, in that case you are getting intercept at Q is equals to 0 is equals to 4. So they are asking what is the value of I absorbed. So let's try to do this question. First of all, what we can do over here is this: from this particular whole thing, we can just use, like, we can just find out first of all that what is the fluorescence intensity. Okay, fluorescence intensity or the rate. So fluorescence intensity or rate will be given by this, that is 0.2 and m star. Now you cannot do anything over here until and unless you are given with the the value of m star. So let's find out the value of m star by applying steady state approximation on m star, because it's an intermediate, right? So d m star by dt. So rate of formation of m star, that is this particular molecule in the excited state, rate of formation from the first step, it depends upon what? It depends upon I absorbed, because it is getting formed over here. So we'll write down in the plus sign. So I absorbed. Okay, in the second step, this m star is being decomposed. Okay, so that's why we have to write down that thing in the negative form. So it will be like minus kq, then we have q into m star. Okay, and in the third step you can see that again it is getting decomposed, right? So m star is getting decomposed, so that's why we'll write down negative sign, and it will be like k. So its rate is given, so you don't have to do anything, you just have to write down from there. So 0.2 m star. Okay, now applying steady state approximation, what will happen? That whole of this equation will be actually equal to 0. That means what? You will get I absorbed, and that will be equal to kq into q into m star minus 0.2 m star. That's what you will get. So what will be the value of m star then? So m star, you can just take common from here, that will be equal to I absorbed divided by kq into q and minus 0.2. Alright, so what we have done, we have just taken common m star over here, and we have just divided kq minus 0.2, and that's what we got. Let it be equation number 2 and this be equation number 1. So we can just put the value of equation of m star from equation 2 to equation 1. Okay, so from equation 2 and 1. So we'll be just substituting the value. So fluorescence intensity or the rate of fluorescence intensity is given by IF. So this particular whole thing can be written as IF, and that is equals to 0.2, and the value of m star. Value of m star will write down from here. So this is I absorbed divided by kq into q and minus 0.2. Now remember, in the question they have said that you are plotting actually 1 by IF versus q. So let's reverse this equation. Okay, so let's take the reciprocal. So you'll get 1 by IF on the left hand side. On the right hand side you will get kq into q minus 0.2, and in the denominator you will be having 0.2 I absorbed. Fine. So now you just need to solve this up a little bit and you will just get the answer. Okay, so that's what we got. We just need to solve it a little bit more. So 1 by IF will remain as it is. On the right hand side we can just split up them. So it will be like kq by 0.2, and it will be like q by I absorbed. Okay, and minus here you will be having just 1 by I absorbed, right? Because this 0.2 and 0.2 will cancel out. So what I have done, I have just separated the denominator, that's all. So you are plotting the graph between 1 by IF versus q. So if you just relate it with this, y is equals to mx plus c, so you will get that Okay, so you should get a positive sign, sorry. There should be a positive sign over here, right? I think I'm doing mistakes since the starting. Just a minute, I'll just show. So what mistake I did when we were taking this to the other side on applying steady state approximation. So this will go to the other side with positive sign, and this will also go to the other side with positive sign. So here should be plus, here should be plus, okay, and everywhere it should be plus. So plus sign. So that's why we'll get plus over here as well and here as well. So if you just compare y is equals to mx plus c, so you will get slope, that is m, and that will be equal to kq by 0.2 I absorbed, and intercept will be equal to 1 by I absorbed. So that's what you will get. Now if you again look upon to the question, you will see that it's given that the intercept is equals to 4. That's what is given to you, that is at q is equals to 0. When you put q is equals to 0, this particular whole thing will become 0, and the intercept is equals to 4. That's what is given. So if the intercept is 4, that means 1 upon I absorbed is equals to 4. And what will be the value of I absorbed? So I absorbed will be 1 by 4, or it will be like 0.25. So this will be your answer. Okay, so this is how this question has to be done. If you go to the options, so here is your question, and the option number 2 was your correct option. So this was the question from June 2019 exam based upon kinetics of photochemical reaction. I hope this topic is quite clear to you guys, and you guys enjoyed this video. If you guys like this video, do let me know in the comment section, and do share with your friends. If you are new to this channel, please subscribe to the channel. It just motivates me to make more and much better content for you guys. If you have any suggestion, if you have any request for the next video, you can comment that down, comment that in the comment section. And from my side, that's all guys. Thank you so much for watching, and have a great day. Bye bye.